move to our second sponsor talk. See where is our Huawei friend. I can see the slides, he's coming. Okay, then let's welcome Jung Ming from Huawei.
Yeah.
Thank you.
Thanks for your introduction. So, thanks for your last talk from our partner Meta. It seems that we are in a same direction. And in my talk, I would like to introduce some key technical challenges for AI cluster networks. First of all, I would like to introduce my department is 2012. This is because we 2012 belongs to a research team. So most of our content is about the research directions. And I would like to introduce this kind of challenges, which is also subjects that we are thriving to research. So let's begin from the background. The world is accelerating into a new era of computing power economy driven by artificial intelligence. So the rapid development of AGI and AI inference application brings huge requirements for AI computing infrastructure. As you can see from the left figure that as predicted from the Stargate projects, that the AI would be capable of independently discovering scientific knowledge in 2028. At that time, there would be millions of GPUs required. That means the power consumption of millions of GPU equals 3,500 megawatt, which is as large as 1/4 Georgia Dam. So supercomputing power is a key to super intelligence. And on the other hand, we can see that a variety of AI-related applications driven AI computing power essential factor. As you can see from the figure that for the past year, in terms of the number of tokens, both Google and Microsoft has achieved an annual growth of 64 and 5 times respectively. So we can see that AI is the currently most computationally memory access and communication intensive application in history, far exceeding the capability of a single chip and a single server. So it is necessary to build a larger scale computing infrastructure through more extensive intelligent computing networks. Considering that the total effective computing power of cluster equals single chip computing power multiply cluster scale multiply computational efficiency. So the AI cluster network is very essential to handle the huge requirements of computing power. And the network is a key to breakthrough. But it also faces multiple challenges. As a following, actually, we have listed 6 challenges we are currently striving to research, including high bandwidth SerDes, high capacity switching, large-scale fabric, high throughput transport, short path data movement from the computer architecture, and long-distance connections. So the first challenge is about high bandwidth connections. Actually, as I mentioned, that the network is a key to handle the huge requirements of computing power. Actually, there is a hottest product which is SuperPod or SuperNode, which is primary driving force behind the development of connection technologies. It also raises some requirements on the high bandwidth SerDes. Currently, as you can see from the figure, that our partners like NVIDIA, Broadcom, and Marvell have released a new SerDes chip, 24 gigabit. But for the next, 448 gigabit SerDes, which is also still under primary research. We have concluded two kind of challenges in the next generation of SerDes. The first one is chip technology. Considering that the 448 gigabit SerDes heavily relies on the chip technology, so we need to do some research about the architectural and algorithm innovation. The second one is about the distance challenge. Considering that 448 electric drives distance is below 1 meter, which posing a challenge for electric interconnection, especially for the requirements between the cabinet requiring more than 1 meter. So it makes that intercabinet connections impossible. So for us, for the future, we need to explore some research. We need more researches on the high edge density optical interconnect technologies to address the challenges of process distance, power consumption, and latency. For example, we need to explore the high edge density XPO or OIO technology to reduce the requirements of single channel rates. And also, we need to focus on the high density EIC, PIC optical connector or electrical connectors and some advancing encapsulations. So this is the first challenge. For the next challenge is high capacity switching. Considering that the intelligent computing drives a rapid evolution, especially for the chip switching capacity, reaching over 100 gigabit. But as you can see from the left figure that this is a product from Broadcom that TH4 and TH5 is designed based on single die. But when it comes to TH6, it becomes 1 master die plus 8 IO die. So this means the single die capacity encounters a bottleneck. So when we talk about the solving this kind of bottleneck, we need to break through the limit, Moore's limit. So the industry is moving forward chiplet architecture, like currently the most hottest topic is wafer, this kind of chiplet direction. So if we adopt the chiplet approach, it will require moving forward larger scale integration and more chiplets. Actually, we have concluded some challenges if we need to build a larger scale chiplets. We need to mainly reduce interconnect tax. The first is interconnection and switching overhead between internal dies grow super linearly with scale. So how can we innovate in architecture and reuse resources to reduce chiplet tax? And secondly, following the larger chiplet, the complexity of routing, balancing, flow control, and cache management between internal dies increases super linearly with scale. So how can we reduce speed up ratio? And the third challenge is about large-scale fabric, which is also the trade-off between the scaling demand and the cost of closed technology, topology. When we talk about the single compute chip capability, we can find too much total computing power, the cluster size must scale by X. But when it comes to a switch chip with two tile close, the scaling capability have to degrade by Y square. So to match the requirements of cluster level computing power, we need to pay the cost and especially the cost is super narrow due to the increased switching tires. In order to achieve a large-scale fabric, we need to explore novel topologies to overcome the super-linear scaling law. The good news is that we have designed UB mesh, which has already been published in HC this year. And our UB mesh has considered the traffic locality and high reliability, low cost. And finally, it forms a scheme with a hybrid direct connect plus switched fabric. Our UV mesh has proposed a direction for the future research is that we need a cost-effective, high-performance, and reliable large-scale topologies tailored for AI traffic. But UV mesh is just a start. We need to more research about the topology with 4 innovations, especially with a system-level view, like the FPR, deadlock-free flow control, load balance, QoS, and congestion control, this kind of consideration. So actually, we have just given a system-level challenges for besides the topology. The first one is following the large-scale AI cluster network. We need to consider the structured addressing and lookup to minimize parking overhead. The second is we need to design all-path routing by using the topology unfolding and the topology regularity to maximize the traffic bandwidth. And the third one is about we need to consider the fault handling. Like when there is a fault, we need to design ultra-fast routing convergency to have a better fault handling. And finally, we need to do some research about the topology and the routing-aware flow control, like applying some circle breaking theory for the channel switching. The fourth challenge is about high-throughput transport. Considering that the main part of the AI network is scale-up network. So the scale-up network has a huge difference from the traditional host bus, especially for in terms of the latency, bandwidth, scale, reliability. And we have some good design on the scale-up network like NVLink, UALink, and unified bus, this kind of protocol. And there is some similarity between these protocols that the transport becomes very important. So we have concluded 3 challenges on the transport protocol design for scale-up network. The first one is outstanding resource. As you know that the AI core's outstanding window is too small to support full bandwidth transmission, especially considering that most of the semantic is load store, which is synchronized. So the synchronized instruction will cause some outstanding window bounded. And the second is about the reliability. When we talk about the transport retransmission for memory semantic, especially for the far memory, this kind of problem, it will cause extra cost in chip area and latency. And finally is that we also want to introduce a multipath into the large-scale AI cluster network. So this kind of introduction will pose new challenges to bandwidth, especially for the ordering. And the fourth challenge is about the short path data movement, which is from actually the last challenge is transport, and transport is a kind of data movement from the perspective of computer architecture. So when we think about it from the computer architecture, we can find that the current large language model like DeepSeek has shown that the inference model is gradually moving forward sparsity and hierarchy approaches. As you can see from the figure, that with small data volumes and sparsity transmissions, the collective communication, especially sparse collective communication, is dominated by link and contraplane delays, which cause some flags from data transmission to system architecture and structure. So we need to do some innovation or break through some challenges on the system level platform. Like here, we have concluded 2 challenges. The first one is the traditional CPU-centric architecture has to face multiple protocol conversion and significant control plane overhead. So it is necessary to establish a fully equivalent interconnection architecture to eliminate migration bottlenecks. Like we have proposed the unified bus, which is designed based on the fully peer-to-peer architecture. And the second challenge is about the traditional DMA-based semantic involves multiple HBM data read and write operations. And this kind of operations integrated with the collective communication will cause significant data plane overhead. So it is necessary to establish a short path direct semantic to achieve a HBM bypass. In this case, we can achieve data movement from one computing core to another by maybe 3 steps. And the last but not least challenge is about the long-distance connection, which means, as I mentioned before, the current network has a huge requirements on computing power, and the network, AI cluster network, is become larger and larger. So it raises distributed AI training. As you can see from the right figure, that both USA and China has applied many data centers or AI data computing centers. But unfortunately, we find there are lots of idle computing power remains fragmented. So in this case, we have concluded 3 kinds of challenges. The first one is about the transport. We want to achieve a high throughput transport. So how to scale RoCE across WANs. And the second is about parallelism, how to maximize the efficiency in large-scale computing and communication parallelism. And the last one is scheduling. We need to flexible schedule the computing, networking, and storage resources to achieve a better efficiency. And actually, we have did some experiment in China. As you can see from the left figure, our experiment is based on Huawei Cloud Platform, and we achieved less than 5% performance loss over 100 kilometers, this kind of distance. In this experiment, we have designed a technical stack, just as a reference. We did some scheduling innovation, collective communication, and transport innovation. So this kind of technical stack has achieved a better performance for the long distance training. But it is not enough, because we only consider the 2 points, peer-to-peer, or 3 kinds of 3 points topology, which is very simple. When it comes to a larger topology or more data centers, the problem will become small. So we need to handle the long distance connection challenges in a more systematic way. So this is the end of my presentation. I would like to invite all of you, the community, to join us to do some research about the AI cluster network, especially on the challenges I mentioned before. And thank you for your listening. And I would like to accept some questions.